Welcome to another episode. Before we begin, I'd love for you to share something in the comments. Tell us where you are listening from and what time of night or day it is for you. And if you enjoy these journeys into science and story, consider subscribing so you'll always have a place to return when you want to drift into knowledge. Now, imagine a world without sunrise. A place where no morning ever comes, where the horizon never glows with light. A planet that has slipped away from its parent star, drifting endlessly in the cold, dark sea of the galaxy. These are rogue planets, wanderers without suns. Tonight, we'll follow their story, how they form, how we discover them, what they mean for life in the universe, and why these invisible giants may outnumber the stars themselves. So settle in, let the world slow down. And let's begin with the silent travelers, the rogue planets. When we imagine a planet, we almost instinctively place it in orbit around a star, Earth circling the Sun, Jupiter shepherding its moons as it loops endlessly around that same fiery center. Even when we think of alien worlds, the mind conjures them bathed in the light of some distant sun, glowing faintly red or burning blue. A planet, in our mental map of the cosmos, belongs to a solar system. It is part of a family, tied by gravity to the heart of a star. But not all worlds follow this familiar script. Some have no sunrise, no orbit to trace, no parent star to hold them in place. They are the orphans of the galaxy, drifting endlessly in the darkness between suns. Astronomers call them rogue planets. Others, more poetically, name them wanderers, free-floating planets, or dark worlds. Whatever the label, the reality is unsettling. They are planets, but not part of any solar system. To imagine one is to imagine a world adrift, a sphere of rock and metal, or gas and ice, floating in the endless black ocean of interstellar space. No warmth streaming from above, only the faint glow of distant stars scattered like dust across the sky. A surface locked in an eternal midnight. Oceans, if they exist, sealed under shells of ice. Storms howling across continents that will never see a dawn. Perhaps volcanoes pulse in the dark, glowing red against the black. Perhaps a crust hides an inner heat, where water and chemistry persist in secret. But from the surface, if you could stand there, you would see no sun and no constellation fixed in place, only the slow turning of the galaxy itself. The image is haunting, a lonely Earth drifting without the sun, and it's no longer just the stuff of science fiction or mythology. Rogue planets are real. The universe, it seems, produces them in staggering numbers. At its simplest, a rogue planet is any planetary mass object not bound to a star. It may have been born inside a solar system and then flung away by gravitational chaos, a close encounter with a massive sibling, or the shifting pull of a young star cluster. Or it may have formed directly in the darkness, collapsing out of a cloud of gas just as stars do, only never gathering enough mass to ignite nuclear fusion. Some might be only a little larger than Earth. Others could rival Jupiter. The definition stretches, but the essence remains. They drift freely, unanchored to the light of any sun. The term rogue is relatively modern. Earlier descriptions leaned toward free-floating planets or interstellar planets. In astronomy, words matter, and the choice of rogue suggests something defiant, even menacing. It is not entirely wrong. These worlds defy the image we've held for centuries of what a planet must be. They are not tethered, they do not orbit politely, they go their own way. And they may outnumber the stars themselves. In 2011, a team of astronomers analyzing data from the OGLE, Optical Gravitational Lensing Experiment, survey suggested that there might be at least as many Jupiter-sized rogue planets in the Milky Way as there are stars, hundreds of billions, perhaps more. Later estimates stretched even further, proposing that there could be 2 rogue planets for every star in our galaxy. That means our galaxy, already home to hundreds of billions of stars, may also hold trillions of lonely worlds drifting through the dark. The scale is difficult to picture. Imagine driving across a desert at night, the stars above scattered across the sky. Now imagine that between each of those stars, hidden in the dark, are 2 or 3 invisible worlds, colder than ice, waiting in silence. That is the galaxy we live in. Not just a galaxy of stars, but a galaxy of lost planets. To us, bound to a star and addicted to light, the idea is unnerving. Earth's rhythms, the spin of days, the march of seasons, are written by our orbit around the sun. Life has grown in obedience to this cycle. Without sunlight, our ecosystems would collapse in days. Yet for rogue planets, this is the normal state. Permanent night, endless cold, a surface lit only by the faint glow of galaxies and nebulae, or the fire of its own inner geology. Picture standing on such a world. Perhaps you're on the shore of a frozen ocean, the waves locked solid under a sky so black it seems bottomless. The stars are sharper here than anywhere you've seen them, piercing points of light, unblunted by any atmosphere thick with water vapor or city haze. Across the sky stretches the faint band of the Milky Way, luminous, crowded with billions of suns that are impossibly far away. There is no sunrise to look forward to, no noon, no twilight, only the slow shifting of constellations over months and years as the rogue planet drifts across interstellar space. Some might say such a place is dead, and perhaps it is, but science whispers another possibility: warmth from within. Deep under the crust, radioactive decay of heavy elements could still be generating heat. Pressure and friction might hold subsurface oceans liquid, just as they do on Europa and Enceladus, moons far from the sun. Life, in microbial form, may need only chemistry and time. It does not necessarily need daylight. A rogue planet, though sunless, could still cradle something alive in its hidden seas. This is where the poetry of astronomy meets the cold equations of physics. A world without a sun is not necessarily a world without stories. It is a reminder that nature's imagination exceeds our own. For most of human history, rogue planets were beyond imagination. Ancient astronomers charted the wandering points of light we now call planets: Mercury, Venus, Mars, Jupiter, Saturn, all of them shining because they reflected sunlight. The word planet itself comes from the Greek planets, meaning wanderer. Yet even then, the wandering was relative. They moved against the background of stars, but all still circled the sun. To conceive of a planet without a sun would have been unthinkable. The first glimmers of the idea emerged much later. In the 19th and early 20th centuries, as astronomers debated the stability of planetary systems, a few speculative voices suggested that gravitational chaos might fling planets into interstellar space. The mathematics of celestial mechanics hinted at the possibility. Systems were not perfectly stable. Encounters with passing stars or interactions among giant planets could lead to ejections. But these were mathematical curiosities, not yet taken as reality. In the 1960s and 70s, as exoplanets themselves were still hypothetical, some astrophysicists quietly entertained the notion that space might harbor interstellar planets. The Soviet astrophysicist Vladimir Arnold mentioned the idea of planetary ejection during star formation. In 1975, the American astronomer Fred Hoyle, famous for his steady-state cosmology, mused about planets that might drift between stars, perhaps even carrying life with them. But with no way to observe them, the idea remained speculative. Half science fiction. It was only in the late 20th century, after the discovery of the first confirmed exoplanet orbiting a sun-like star in 1995, 51 Pegasi b, that astronomers began to take the possibility of rogue planets more seriously. If planets were this common, the reasoning went, then instability must also be common. Young systems fling out their excess worlds like children scattering toys. And if so, the galaxy must be littered with planetary castaways. The first real observational hints came in the early 2000s. Surveys of young star clusters using infrared telescopes detected objects too small to be stars, too massive to be brown dwarfs, wandering alone. Some appeared to be only a few times the mass of Jupiter. These detections were controversial. Were they failed stars or true planets? But they cracked open the door to the idea that the galaxy's population of planets was not confined to solar systems. Then came the gravitational microlensing surveys. Using Einstein's theory of general relativity, astronomers realized that even a dark object could be detected by its gravity bending the light of a background star. In 2011, a team analyzing data from the OGLE and MOA, microlensing observations in astrophysics, collaborations, reported evidence for a large population of unbound Jupiter mass planets. Their paper, published in Nature, suggested that the Milky Way might host twice as many rogue planets as stars. The astronomical community took notice. Suddenly, rogue planets were not curiosities, they were everywhere. What had once been only a haunting thought experiment became a new field of research. Telescopes began to hunt the dark. Simulations tried to model the chaotic ballet of young planetary systems ejecting their children. And science fiction, which had always been quicker to imagine, suddenly had real physics to back its stories of worlds adrift. It is difficult not to feel a chill when considering them. Not the chill of science, but of perspective. To know that beyond the constellations, hidden in the black between stars, there are worlds by the trillion, unseen, unknown, drifting in silence, planets without suns. And with that haunting truth, we turn from what rogue planets are to how they are born. Long before telescopes, before spectroscopy or space probes, the sky was already a stage for imagination. To the ancients, the night sky seemed ordered, eternal, and unchanging. The stars wheeled in precise patterns, their positions predictable, their cycles reliable. But there were a few luminous points that defied this order. They wandered. From one night to the next, their paths shifted, slipping across the fixed backdrop of constellations. To Greek philosophers, they were planets asteres, wandering stars. These wanderers, what we now call planets, were mysterious because they refused to stay in their place. While most stars appeared eternal, these bodies were restless, erratic, untethered. Of course, no one in ancient Athens or Babylon thought of them as worlds like Earth. They were lights in the sky, gods walking among the constellations, omens for kings and empires. Mars, reddish and fierce, was associated with war. Venus, bright and beautiful, became the goddess of love. Jupiter, immense and slow-moving, was a regal presence, king of the heavens. Even so, the seed of the idea was there. Some celestial lights do not obey the rules. They wander, and for a long time, that was enough to inspire awe, worship, and sometimes fear. The concept of a planet without a sun would not have fit into their cosmology. For Aristotle, the universe was composed of crystalline spheres, each carrying its lights around the Earth. Everything had its place, its orbit, its purpose. To be unbound from that system would have been inconceivable. The cosmos was order, not chaos. And yet, chaos was hiding in the mathematics all along. The first cracks in that ancient worldview came with Copernicus in the 16th century. By placing the sun at the center and Earth among the wanderers, he turned the universe inside out. Suddenly, planets were not just moving points of light, but fellow worlds, sharing the same central star. Galileo, peering through his small telescope in 1609, saw moons circling Jupiter, spots on the sun, mountains on the moon. The heavens were not perfect after all. They were dynamic, restless, full of surprises. Kepler and Newton deepened this vision, showing that planetary motion followed precise mathematical laws of gravity. Planets circled their suns in ellipses, pulled in by the invisible force that also governed falling apples. It was a universe governed not by divine spheres, but by physics. And once physics enters the picture, new possibilities emerge. If gravity could bind planets to stars, it could also unbind them. A close encounter between two massive planets, or the passage of a nearby star, could eject a world into interstellar space. The mathematics allowed it, even if no one had seen such a thing. By the 18th and 19th centuries, astronomers began to suspect that the universe might be less stable than Newton's clockwork implied. The French mathematician Pierre-Simon Laplace studied the long-term stability of the solar system and found it delicately balanced, subject to resonances and perturbations. The American astronomer Simon Newcomb, in the 1890s, suggested that even small instabilities over vast timescales could fling planets away. The seeds of rogue planets were there, hidden in the cold logic of celestial mechanics. In popular imagination, though, it was often literature that reached for the idea first. The 19th century was full of speculative fiction about dark companions and wandering worlds. Camille Flammarion, the French astronomer and author, wrote about infinite worlds and cosmic collisions. H.G. Wells, in The Star, 1897, described a rogue object passing close to Earth, disturbing tides and climates, nearly destroying the planet. These stories drew on the growing awareness that space was not empty and orderly, but alive with movement, encounters, and risks. Still, in the scientific community, the notion of planets without stars was fringe. For a planet to exist, it was assumed it must orbit a sun. Without sunlight, how could such a world even be visible, let alone survive? The idea seemed closer to myth than physics. The 20th century began to change that. As astrophysicists began modeling star formation more precisely, they realized that planetary systems are messy. In the 1940s and 50s, theories of accretion and protoplanetary disks suggested that young systems might form far more planets than they keep. Giant planets could migrate inward, disrupting smaller neighbors. Collisions were common. Worlds could be thrown into eccentric orbits or hurled into interstellar exile. By the 1960s, a few bold voices began suggesting that free-floating planets might exist in significant numbers. The Soviet astrophysicist Vladimir Arnold hinted at planetary ejection during the violent early years of solar systems. The American astrophysicist Michael Ovenden argued that instability was an essential feature of planet formation, not a rare accident. And in 1975, Fred Hoyle, the controversial but brilliant British cosmologist, suggested that planets might drift through the galaxy unbound, some even carrying life. Hoyle's broader theories were often criticized, but his suggestion struck a chord. If nature is wasteful, then surely many planets are cast adrift. The problem was evidence. How could one detect something invisible? A planet without a sun produces no reflected light, no solar-powered glow. Unless it passed very close to Earth, it would remain unseen. For decades, rogue planets stayed in the realm of thought experiments and speculative equations. It took a revolution in exoplanet astronomy to change the picture. In 1992, Alexander Vulshan and Dale Frail discovered the first planets outside our solar system, orbiting a pulsar, of all things, 2,300 light-years away. Then, in 1995, Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, the first planet orbiting a sun-like star. The universe suddenly was crowded with worlds. Theories that once seemed daring became common sense. If planets are everywhere, they must also exist in every state, including exile. By the late 1990s, telescopes searching star-forming regions began finding objects too small to be stars, yet not bound to any system. Some were brown dwarfs, failed stars that never ignited, but others were lighter still, planetary mass, wandering alone. Were these true rogue planets, or simply the smallest of stars? The boundary blurred, but the implication was clear. The cosmos contained objects outside the neat categories of sun and planet. Then came the breakthrough: gravitational microlensing. Einstein's general relativity predicted that massive objects bend light. Even a dark planet passing in front of a distant star would briefly magnify its light. In the 2000s, collaborations like OGLE and MOA began to search for these fleeting distortions. And in 2011, astronomers announced something extraordinary: a population of Jupiter-mass objects drifting freely through the Milky Way, perhaps as numerous as the stars themselves. It was a turning point. For centuries, planets had been tied, in human thought, to stars, first as wandering lights circling Earth, then as worlds orbiting the Sun, then as exoplanets circling alien stars. Now, the image had shifted again. Planets did not need suns. They could wander alone. This shift was not just scientific, but philosophical. To imagine a rogue planet is to challenge our assumptions about belonging. Earth feels secure because it belongs to the Sun, its orbit steady, its light dependable. But the cosmos, as it turns out, produces countless worlds that belong to no one. They are homeless, sunless, drifting. And if planets can be exiled, so too can our understanding of stability and permanence. Looking back, it seems inevitable. From the Greeks naming wanderers in the sky, to Newton's laws revealing that orbits are fragile, to 20th century astrophysicists speculating on planetary ejections, the story was waiting to unfold. The discovery of exoplanets in the 1990s was the key that unlocked it. Once we knew that planets were not rare jewels, but common pebbles in the cosmic river, it became impossible to doubt that many must also be lost along the way. Rogue planets, in that sense, are not an exception to the rule. They are the rule taken to its conclusion. Planets form, they orbit, they collide, they migrate, they are flung away. The galaxy is not a tidy family portrait of stars with their retinues of obedient worlds. It is a dynamic, turbulent ecosystem, full of castaways. The ancients were right about one thing: some lights in the heavens wander. What they could not have known is that the greatest wanderers of all are invisible, moving silently between the stars, waiting for us to discover them. When a planet drifts without a star, the question naturally arises: how did it end up there? Was it born in darkness or cast out from the light? To understand the origins of rogue planets, we need to peer into the turbulent birthplaces of worlds, the lives and deaths of stars, and the restless dynamics of the galaxy itself. The making of a planetary system is not a gentle process. It begins in chaos, a cloud of gas and dust collapsing under gravity, swirling into a rotating disk around a newborn star. Within this disk, dust grains collide and stick, growing into pebbles, then boulders, then planetesimals, objects kilometers across. These clump into planetary embryos, and through collisions and accretion, into full-fledged planets. From a distance it may look elegant, but up close it is violent. Worlds form by smashing together, merging, scattering one another, reshaping orbits in unpredictable ways. This chaos is the first and most prolific source of rogue planets. In a young system, the dance of gravity can be ruthless. Imagine a newly formed giant planet, say, a body 10 times the mass of Jupiter, swinging inward toward the star. Its immense gravity disturbs everything around it, flinging smaller worlds aside. Some are swallowed by the star, some collide with each other, and some are slingshotted outward, accelerated past escape velocity, launched into interstellar space. This process is called gravitational scattering, and it is one of nature's favorite tricks. The mathematics of scattering are elegant in their cruelty. If two planets of unequal mass pass close to one another, the smaller is more likely to be ejected, while the larger settles into a slightly altered orbit. The system preserves momentum by sacrificing the weaker body. Astronomers running simulations of planetary formation find that this outcome is not rare, but common. For every solar system that ends up looking stable, like ours, there may be many more where worlds are thrown away like excess debris. Even our own solar system may have been guilty of such an act. Some models of its early evolution suggest that Jupiter, Saturn, Uranus, and Neptune did not always reside where they are now. They may have migrated dramatically, with Neptune moving outward and Uranus shifting, scattering countless smaller bodies in the process. In some simulations, an additional ice giant, perhaps the size of Neptune, was present, only to be ejected entirely, banished into the galaxy as a rogue. If true, then somewhere in the darkness between the stars drifts a lost sibling of Earth, born under the same sun, but doomed to wander forever. Yet scattering is not the only pathway. Stars themselves can betray their planets. Consider what happens when a star dies. A massive star, many times the mass of the Sun, will explode in a supernova at the end of its life. In an instant, much of its mass is blown away. The gravity that bound its planets weakens. If the star loses enough mass, the planets can no longer be held, and they drift away. Even less dramatic endings, like our own Sun's eventual death, can set planets free. In about 5 billion years, the Sun will swell into a red giant, engulfing Mercury and Venus, perhaps Earth. Later, it will shed its outer layers and collapse into a white dwarf. As its mass drops, the orbits of the surviving planets will expand. Some may escape entirely, set loose to become rogues. Stellar death, then, is another great contributor to the galaxy's population of wanderers. There are also quieter exiles. In dense star clusters, where newborn stars crowd close together, planets live in precarious neighborhoods. A passing star can tug on a system's outer planets, stealing one away or flinging it into space. Over millions of years, these encounters add up. The galaxy is a vast web of gravitational interactions, and planetary systems are not sealed. They are porous, vulnerable to disruption. In this way, galactic dynamics act as a slow but constant source of rogue planets. Migration adds another layer to the story. Planets are not always born where we find them. In fact, one of the great surprises of exoplanet astronomy has been the discovery of hot Jupiters, giant gas planets orbiting scorchingly close to their stars. Such planets cannot form so near. They must have migrated inward from cooler, outer regions. Migration is thought to be driven by interactions with the protoplanetary disk or with other planets, and migration, by its nature, is destabilizing. As one body shifts inward, others are perturbed, some hurled outward into eccentric orbits, some thrown entirely free. A galaxy filled with migrating giants is also a galaxy filled with ejected exiles. The statistics reinforce the violence. Simulations suggest that in a typical planetary system, one or more planets are ejected during its early evolution. Multiply this by hundreds of billions of stars in the Milky Way, and the result is staggering. Rogue planets are not rare accidents. They are the normal byproducts of planetary birth. Just as every tree produces seeds that never take root, every star system produces worlds that never find a home. Some of these rogues may be large, gas giants as massive as Jupiter, or even heavier. Others may be small, rocky worlds the size of Earth or Mars. Detecting them is difficult, but theory does not discriminate. Any mass can be exiled. In fact, small planets may be ejected more easily, their lower gravity making them more vulnerable to scattering. It is possible that among the trillions of rogues in our galaxy, many are Earth-sized, drifting in perfect darkness, carrying with them the chemical ingredients of life. There is also the possibility of worlds formed in darkness from the very beginning. Just as stars form by the collapse of a gas cloud, so too can substellar objects, brown dwarfs, form by direct collapse. If the collapsing fragment is too small to ignite fusion, it becomes a failed star. But what if it is smaller still, in the range of planetary masses? Then it is not a failed star, but a planet born without a sun. These free-born planets blur the line between star and planet, between formation by collapse and formation by accretion. Some astronomers argue that if an object forms this way, it is technically a sub-brown dwarf, not a planet. Others reply that the distinction matters less than the outcome, a world adrift, indistinguishable in its isolation from an ejected planet. The galaxy, then, is filled with wanderers born of many stories. Some are victims of violence, flung away by their siblings. Some are orphans of dying stars. Some are children of chaos, born in the dark with no parent to orbit. All end in the same condition, alone, drifting between suns. To grasp this is to shift how we see the universe. For centuries, we imagined stars as the dominant population, with planets as their attendants. Now we know that planets may outnumber stars, and that a significant fraction are wanderers. The Milky Way is not a neat map of solar systems. It is a restless ocean with islands of light, stars with their planets, and vast currents of darkness carrying worlds that will never see a sunrise. If we could chart them, the picture would be astonishing. Between us and the nearest star, Proxima Centauri, there may be dozens of rogue planets drifting unseen, each the size of Mars, or Earth, or Jupiter, each with its own geology, its own history, its own fate. A silent population, invisible to our eyes, yet shaping the statistics of the galaxy. They may collide with stars, skim past systems, or drift forever in solitude. Each one is a story of formation, ejection, survival, and in a way, their existence makes our own situation more precious. Earth is not guaranteed safety. Our orbit, stable now, is the product of billions of years of cosmic accidents that might have turned out otherwise. We could have been scattered, cast off, frozen in the dark. That we orbit a warm, steady star is not inevitable. It is a stroke of cosmic fortune. When we consider rogue planets, we are reminded that the universe is not built for comfort. It is dynamic, unstable, filled with motion and exile. But from this chaos emerges the diversity of worlds, the possibility of life, and the haunting beauty of planets that wander without suns. How do you find something that doesn't shine? That is the central problem of rogue planets. Ordinary planets are already elusive. Even ones that orbit stars are tiny and faint compared to the suns they circle, their light drowned in the glare. To detect them, astronomers often rely on indirect clues, tiny dips in starlight, subtle wobbles in a star's motion. But what about a planet with no star at all? A world drifting in darkness, offering no transit, no wobble, no reflection. How could such a thing ever be found? It seems impossible. And yet, astronomy has a long tradition of turning impossibility into discovery. The first great tool in this hunt comes from Albert Einstein. In 1915, Einstein published his theory of general relativity, rewriting our understanding of gravity. No longer was gravity a mysterious force acting at a distance. It was the warping of space and time by mass. A star bends the fabric of space-time, and light, traveling along that fabric, bends with it. For a while, this was considered a purely theoretical insight, something elegant but unreachable by observation. But in 1919, during a solar eclipse, Arthur Eddington and his team famously measured starlight bending around the sun, confirming Einstein's predictions. Gravity could bend light. That same principle, magnified across the galaxy, became a tool for finding the unseeable. If a massive object, say a rogue planet, passes in front of a distant star, its gravity bends and focuses the star's light. For a brief moment, the star appears to brighten, as if a cosmic magnifying glass has passed in front of it. This effect is called gravitational microlensing. The beauty of microlensing is that it does not require the planet to shine. The planet could be as black as coal, as cold as interstellar space. It doesn't matter. Its mass is enough. When it drifts across the line of sight, space itself acts as the detector. The background star flares brighter, then fades back to normal, leaving astronomers with a fleeting signature of something invisible. But there is a catch. These events are rare and unpredictable. The alignment must be nearly perfect. The rogue planet, the distant star, and the Earth-based observer all in just the right geometry. And the event is temporary, sometimes lasting only hours or days. Astronomers must survey millions of stars, waiting for the cosmos to stage one of these chance alignments. It is like watching a crowded night highway, hoping that once in a while, two headlights line up exactly behind a lamppost. Despite the challenge, microlensing has proven astonishingly effective. The Optical Gravitational Lensing Experiment, or OGLE, based in Chile, has monitored the sky since the 1990s. Its wide-field telescopes scan the dense star fields of the Milky Way's central bulge, watching for tiny, brightening events. The Microlensing Observations in Astrophysics Project, or MOA, based in New Zealand, does the same, offering coverage from another hemisphere. Together, these collaborations have caught hundreds of lensing events, including ones too short to be caused by stars or brown dwarfs. The only reasonable explanation: rogue planets. In 2011, a joint analysis of OGLE and MOA data revealed evidence for a large population of unbound Jupiter-mass planets. The team reported their results in Nature, estimating that these wandering giants could be as common as stars in the Milky Way. It was a stunning revelation. For decades, rogue planets had been theoretical curiosities. Suddenly, they were statistically unavoidable. Microlensing has since remained the most powerful tool for detecting these elusive wanderers. In 2020, astronomers announced the detection of a candidate rogue planet smaller than Earth, possibly the lowest mass free-floating planet ever found, based on a microlensing event that lasted only 41 minutes. Such discoveries remind us that rogue planets are not just enormous gas giants. They may also be small, rocky worlds, hidden by the millions, drifting unseen. And yet, microlensing is only one approach. Another path is to search for what faint light rogue planets may emit on their own. Even in the absence of a star, a planet may glow, dimly but detectably, in infrared. Young rogue planets, in particular, are still warm from their formation, radiating heat like cooling embers. If a telescope is sensitive enough in the infrared, it can spot these faint beacons against the cold backdrop of space. The challenge is enormous. Infrared light is easily absorbed by Earth's atmosphere. So many searches must be conducted from space or at high-altitude observatories. And even then, the sky is crowded with faint sources, brown dwarfs, dust clouds, distant galaxies, all glowing in the infrared. Distinguishing a rogue planet requires precise measurement of mass and motion, often by combining infrared surveys with microlensing or parallax measurements. Still, progress has been made. The Wide Field Infrared Survey Explorer, WISE, launched by NASA in 2009, conducted an all-sky infrared survey. Among its many discoveries were dozens of nearby brown dwarfs and hints of objects with planetary masses. Later surveys of star-forming regions, like the Orion Nebula, revealed isolated objects only a few times the mass of Jupiter, glowing faintly in infrared. Were these failed stars or true planets? The line is blurred, Yet, either way, they proved that nature can produce small, sunless worlds. Kepler, the famous planet-hunting spacecraft, played a smaller but still notable role. While its main mission was to detect planets by the transit method, tiny dips in starlight caused by planets crossing in front, its vast data set of stellar variability and faint objects provided context for microlensing campaigns. Kepler itself was not well suited to finding rogue planets directly, but it helped refine the statistics. If so many planets orbit stars, then many must also be ejected. Later missions, like K2 and TESS, continued this statistical work, narrowing estimates of planetary populations. The real promise lies in the future. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will carry a wide-field infrared survey capability, specifically designed to exploit microlensing on a grand scale. Roman is expected to find hundreds of rogue planets, from giants to Earth-mass bodies, and finally provide robust statistics on their abundance. ESA's Euclid mission, launched in 2023 to study dark energy, will also contribute using its precision surveys to catch microlensing events. Together, these missions will transform rogue planets from curiosities into a catalogued population, mapped and counted. Yet, even as we prepare for that flood of data, there is something poetic about the methods themselves. To find planets that do not shine, we rely on distortions in the light of distant stars, or the faint whisper of heat left over from their birth. We never see them directly. We see their shadows, their fingerprints, their brief gravitational signatures as they pass across our sightlines. They remain hidden, and yet their presence is undeniable. This makes the search for rogue planets feel almost mythological. For centuries, humans told stories of invisible wanderers, ghost ships adrift on the sea, lost souls wandering between worlds. Today, science gives us their modern equivalents, planets we cannot see, yet know to exist, drifting in eternal night. The methods we use to find them, Einstein's bent light, infrared whispers, feel like instruments for detecting ghosts. And in a way, they are. But these ghosts are real, and their discovery forces us to rethink the galaxy. The sky we see at night is only a fraction of what is there. Between every star, there are worlds we cannot see, revealed only in fleeting distortions of starlight or faint traces of heat. The universe is not empty between suns. It is populated with wanderers, waiting for us to notice them. The first time astronomers announced that rogue planets might be as common as stars, the claims sounded almost absurd. For centuries, planets had been thought of as rare companions, jewels that circled their suns like loyal attendants. To say that the galaxy could contain more starless worlds than stars themselves seemed almost like heresy. And yet, as the data accumulated, the numbers pointed in only one direction. Rogue planets are not just real, they are abundant, perhaps staggeringly so. The breakthrough came in 2011. A team analyzing data from two long-running microlensing surveys, OGLE and MOA, studied the subtle brightening of millions of background stars. Out of this vast data set emerged events that could not be explained by stars or even brown dwarfs. The timescales were too short, the masses too small. The best explanation was that Jupiter-mass objects were drifting freely, unbound to any star. Writing in Nature, the team estimated that these wanderers might be at least as common as the stars in the Milky Way. If correct, that meant hundreds of billions of rogue planets in our galaxy alone. It was a staggering claim, and one that sparked immediate debate. Could it really be that every star in the Milky Way had, on average, one or two planetary exiles drifting in its wake? If true, the galaxy was not a map of bright islands surrounded by emptiness. It was an archipelago dotted with invisible worlds, more numerous than the suns themselves. Other studies soon backed the claim. Simulations of planetary formation showed that ejection was a normal byproduct of chaos. If every planetary system began with a crowded disk of young planets, then scattering and expulsion would be inevitable. Some studies suggested that for every star, multiple planets might be lost to interstellar space. The galaxy, far from being mostly empty between stars, could be thick with exiled worlds. Among the discoveries, a few stand out as milestones. In 2006, Ogle detected a microlensing event that revealed an object later named Ogle 2006 BLG 192LB. The planet was only a few Earth masses, orbiting what appeared to be a very low-mass star or brown dwarf. Though not entirely free-floating, it hinted at how small planets could survive or drift near stellar remnants, straddling the line between bound and rogue. Its importance lay in showing that planets could exist in extreme, unexpected circumstances, broadening the definition of where and how they could form. The 2011 study itself did not identify individual planets by name. Instead, it presented a statistical argument for a vast, unseen population. That was powerful in itself. Astronomy had gone from speculation to numbers, from myths of wandering worlds to actual census counts. And the numbers were huge. In 2019, the field advanced again. Microlensing campaigns, now more sensitive and covering wider sky regions, began detecting shorter and shorter lensing events. These timescales corresponded not to gas giants, but to smaller, Earth or Mars-sized planets. One event in particular, lasting only a few hours, suggested the presence of a rogue planet with a mass close to Earth's. If confirmed, this would be the first detection of a terrestrial rogue, a reminder that exile is not reserved for giants. Small, rocky worlds, too, may drift in the dark by the billions. Each new discovery reshapes how we view planetary systems. Before the 1990s, we had only one example, our own. The discovery of hot Jupiters shattered assumptions about what orbits were possible. The discovery of super-Earths revealed a class of planets missing from our solar system. And the discovery of rogues showed that planetary systems are not sealed boxes, but leaky, unstable, full of collisions and expulsions. Planets are not always permanent residents. Some are temporary tenants, eventually cast into the galaxy at large. What these discoveries reveal is both sobering and inspiring. First, they tell us that planetary formation is messy. A star does not quietly gather its family of planets and then settle into eternal stability. Instead, there is conflict, migration, and betrayal. Some planets spiral into the star, others collide, others are scattered outward, and some escape altogether. Our own solar system, with its long-lived orbits, is the exception, not the rule. Second, the discoveries suggest that habitability may be stranger than we thought. If rogue planets are common, then the inventory of potential abodes for life expands enormously. Even if only a fraction have subsurface oceans or thick insulating atmospheres, the sheer numbers mean that life might find niches in places we once thought impossible. 1 trillion planets offer 1 trillion experiments in survival. Third, rogue planets remind us of the fragility of orbits. Our world feels stable, anchored to the sun. But stability is relative. Given the right perturbation, a wandering star, a gravitational resonance, Earth itself could, in theory, be nudged into exile. It is not likely, but it is not impossible. The discoveries of rogues make this clear. Exile is part of the cosmic story. What about their role in galactic architecture? If the Milky Way contains trillions of rogue planets, they add mass to the galactic disk. Not enough to account for dark matter, rogues are far too small and too warm, but enough to matter for the dynamics of stars and clusters. They are part of the invisible skeleton of the galaxy, contributing mass without contributing light. The excitement now turns to the future. The Nancy Grace Roman Space Telescope is expected to detect hundreds of rogue planets via microlensing, providing the first real catalogue instead of statistical hints. Some may be Earth-sized, others giants. With enough data, astronomers hope to test models of planetary ejection, constrain the frequency of rogue Earths, and even ask whether free-floating planets outnumber bound ones. Euclid, already scanning the skies, will likely provide supporting data. Together, they will transform our understanding from speculation to certainty. In a way, the discoveries so far are just the shadows on the wall. Microlensing gives us glimpses. Infrared surveys show us the warmest, but the true population is still invisible. Yet even those glimpses have changed the narrative. Rogue planets are no longer a curiosity whispered in theory papers. They are a fundamental component of the galaxy, woven into its structure as much as stars and dust. To think of the Milky Way now is to think not just of constellations of light, but of invisible constellations of darkness, billions of planets drifting, unseen, between the suns. Each discovery sharpens that picture, each detection another ghost illuminated by physics. And with every new number, every new candidate, we realize how incomplete our old view was. The cosmos is stranger, fuller, and far more crowded than we ever imagined. Life, as we know it, is addicted to light. On Earth, the sun is everything. The source of warmth, the clock of our days, the engine of photosynthesis that feeds forests, oceans, and us. Strip the sun away, and our world collapses in hours. Within a week, most plants would wither. Within months, the oceans would freeze across their surfaces. Within years, Earth would be encased in ice, a dead marble adrift. It seems obvious. Without a star, there can be no life. And yet, science has a habit of overturning the obvious. Consider the depths of Earth's oceans. Far below the reach of sunlight, at depths where no photon has penetrated for millions of years, there are ecosystems thriving around hydrothermal vents. These vents belch heat and chemicals from Earth's interior, and around them swarm creatures that would look alien if they weren't here on our own planet. Giant tube worms, pale crabs, fish with translucent skin, microbial mats feeding on sulfur instead of sunlight. These organisms do not use photosynthesis. They use chemosynthesis, pulling energy not from the sun but from chemistry. When scientists first discovered these vent communities in the late 1970s, it was a revelation. It proved that life could be powered not by starlight, but by geology. Suddenly, a sunless planet didn't look quite so sterile. If Earth could support ecosystems without the sun, perhaps rogue planets could too. The first question is energy. A rogue planet drifting in interstellar space receives almost no heat from stars. Its surface would quickly radiate away the warmth of its formation. But planets are not just passive bodies. They have interiors. Earth, for example, is still hot inside, its core at thousands of degrees Celsius. Some of that heat comes from leftover energy of formation, but much comes from radioactive decay of heavy elements like uranium, thorium, and potassium. As these isotopes break down, they release heat, keeping Earth's interior molten and driving plate tectonics. This same radioactive furnace would continue to burn inside a rogue planet. It may not be enough to keep the surface warm, but it could keep water liquid underground. Beneath an insulating crust of ice, a hidden ocean might persist for billions of years. We already know this is possible because it happens in our own solar system. Europa, one of Jupiter's moons, and Enceladus, orbiting Saturn, both have thick ice crusts with liquid water beneath. Their heat comes partly from tidal flexing, the gravitational pull of their giant planets stretching and kneading them, but also from radioactive decay. On Enceladus, jets of water vapor and ice crystals have been observed shooting into space from cracks in its surface, proof of an active subsurface ocean. Now imagine the same scenario on a rogue Earth. Once exiled, its surface would freeze, but below kilometers of ice, heat from radioactive decay and residual internal warmth could keep oceans liquid. If hydrothermal vents dotted the seafloor, just as on Earth, they could supply the chemistry needed for life. Microbes could evolve to harness that energy, feeding ecosystems hidden away in total darkness. They would never see the stars. They would never know their world was drifting through the galaxy. For them, the crust above would be a ceiling, the vent a sun, the ocean an entire universe. In 1999, astrophysicists David Stevenson and Eric Abbott proposed that rogue planets could indeed host subsurface oceans kept warm by internal heat, especially if blanketed by thick atmospheres of hydrogen. Hydrogen, being an excellent insulator, could trap heat and prevent the planet from freezing entirely. In such a case, a rogue planet might even retain surface oceans, not just subsurface ones. It would glow faintly in infrared, a lonely ember in the dark. Such a planet would be alien, but not lifeless. Life, if it emerged there, would not resemble life that depends on photosynthesis. It would be chemotrophic, feeding on chemical gradients. It would be microbial, at least at first, but evolution has no obligation to stop at microbes. On Earth, whole ecosystems flourish without sunlight, and multicellular life has adapted to the deep sea. On a rogue planet, the constraints would be harsher, but not impossible. The idea that life could exist on rogue planets has enormous implications for astrobiology. If there are billions or even trillions of such worlds in the Milky Way, then the number of potential habitats for life increases by orders of magnitude. We usually think of habitable zones as narrow bands around stars, the Goldilocks zone where liquid water can exist on the surface. But rogue planets suggest a different kind of habitable zone, one internal, driven by geology and chemistry, not distance from a sun. In this view, habitability is not tied to starlight at all. It is tied to energy, in whatever form it comes. Europa and Enceladus are proof of concept. Neither receives enough sunlight for habitability, yet both almost certainly harbor liquid water and chemical energy sources. If such conditions exist around small moons in our solar system, why not around full-sized rogue planets adrift in the galaxy? Speculative though it may sound, this idea has gained traction among serious scientists. In 2000, Stevenson proposed that rogue planets with thick hydrogen atmospheres could be surprisingly temperate, with surface oceans remaining liquid for billions of years. In 2003, Abbott and Switzer argued that such planets might even be easier to detect than we thought, glowing in the infrared as warm worlds wandering the dark. Their work reframed rogues not as dead rocks, but as potential cradles of biology. Still, questions remain. Could life originate in such conditions, or would it require seeding from elsewhere? Panspermia, the hypothesis that life can travel between worlds via comets or meteorites, offers one possibility. A rogue planet passing through a dense star-forming region might be bombarded by icy bodies carrying organic compounds, kick-starting chemistry in its hidden seas. Or life might arise independently, as it did on Earth, from the raw ingredients of water, heat, and chemistry. Science fiction has long loved this idea. Writers imagined frozen planets with glowing caverns beneath, civilizations adapted to endless night, organisms feeding on chemical heat. Arthur C. Clarke once speculated about life on Europa long before we confirmed its ocean. In fiction, rogue planets often appear as mysterious interlopers, passing close to Earth and stirring chaos. In reality, they may be quieter, hidden cradles of life, carrying their secrets across the galaxy. But let us be careful. The conditions are harsh. A rogue planet without a thick atmosphere might be nothing but a frozen rock, sterile and silent. Even with internal heat, subsurface oceans may not last forever. As radioactive isotopes decay, their energy output diminishes. After billions of years, a planet's core cools and its oceans may freeze solid. Life would need not only to emerge, but to adapt and survive through this slow decline. Yet the possibility remains intoxicating. Life, if it can endure on rogue planets, would be proof that biology is not tied to stars. It would mean that the universe is littered with habitats invisible to us, hidden in the darkness between suns. The search for life would no longer be confined to bright orbits around stars, but extended to the great black wilderness of interstellar space. What would such life look like? On Earth, vent communities thrive on sulfur, methane, hydrogen. Microbes exploit gradients of chemistry as efficiently as plants exploit gradients of light. They form mats, biofilms, colonies that build up complexity. Some bacteria use iron, others use arsenic. Life is astonishingly adaptable, a chemist without prejudice. On a rogue planet, microbes might evolve around similar processes. Perhaps giant vent chimneys line the seafloor, dripping with colonies of extremophiles. Perhaps larger creatures graze on these microbes, blind but guided by chemistry or heat. Evolution, given time, could produce ecosystems unrecognizable to us. The haunting thought is this: these biospheres, if they exist, would be completely cut off from the galaxy. No star to light their skies, no outside world to notice them. Entire civilizations of microbes could live and die without ever knowing there was such a thing as sunlight. The galaxy could be full of such secret worlds, their oceans swarming with life, invisible to all but themselves. The comparison to Europa and Enceladus is crucial. These moons are not rogue planets, but they show that life may not require stars. When the Cassini spacecraft flew through Enceladus's plumes, it detected organic molecules, water vapor, and salts, ingredients for habitability. On Europa, the Galileo mission measured magnetic signatures consistent with a salty ocean beneath the ice. If moons can do it, so can planets. A rogue world is just a bigger version, with more mass, more heat, more chances for chemistry. It is almost poetic. Exile does not mean death. In solitude, life may find a way. The question, of course, is how we could ever know. Detecting life on a rogue planet seems, for now, beyond our reach. We can infer their presence by microlensing, detect their faint heat in infrared, but probing their oceans is another matter entirely. They are too far, too dark, too hidden. For the foreseeable future, life on rogue planets will remain a hypothesis, not an observation. But hypotheses matter. They expand our imagination, guide our instruments, and remind us that the universe is richer than we think. 50 years ago, no one would have believed in billions of exoplanets. 30 years ago, no one would have bet on oceans beneath icy moons. Today, both are facts. Perhaps tomorrow, rogue planets with life will join them. For now, we can only speculate. But it is speculation grounded in science, sharpened by examples in our own backyard. Europa whispers that life can survive without sunlight. Enceladus sprays its secrets into space. Earth's own vents prove that biology can thrive in darkness. Rogue planets, it seems, are not barren. They are possibilities. And there is something strangely comforting in that thought. As our telescopes look outward and our theories reach further, we begin to see the galaxy not as a desert, but as a wilderness filled with hidden oases. We may never visit most of them. We may never even detect them directly. But the knowledge that they are there, that exile can still harbor life, changes how we see existence itself. The night sky looks empty between the stars, but in that emptiness, billions of planets drift, and on some of them, perhaps, life stirs in hidden oceans, oblivious to the absence of light. Science can tell us what rogue planets are, how they form, and how we might detect them. But long before the first microlensing survey, long before astrophysicists estimated trillions of such worlds, the idea of dark wanderers was already alive in human imagination. Fiction, myth, and philosophy gave them a home, long before telescopes could. In a way, rogue planets are not only scientific discoveries, they are archetypes, symbols of exile, solitude, and the defiance of order. Writers and storytellers have always been drawn to the idea of worlds unmoored. Even in the 19th century, as astronomy was just beginning to glimpse the vastness of the galaxy, authors speculated about dark bodies passing close to Earth, altering its fate. In H.G. Wells's story, The Star, 1897, a wandering celestial body passes near our planet, bringing floods, earthquakes, and apocalyptic changes. It is not exactly a rogue planet as we define it now, but the seed is there, the fear of something massive and invisible drifting out of the night. To readers of the time, still clinging to the notion of a tidy, clockwork cosmos, such a scenario was both terrifying and thrilling. As science fiction matured in the 20th century, rogue planets became recurring characters. In Arthur C. Clarke's Rendezvous with Rama, 1973, humanity encounters an interstellar object passing through the solar system. Though it is a spacecraft, not a planet, Clarke was fascinated by the idea of things adrift between stars. Later, in The Songs of Distant Earth, 1986, he explored the loneliness of exile in deep space, reflecting the same themes that rogue planets symbolize: detachment, survival in darkness, the longing for connection. Isaac Asimov, too, brushed against the idea. In Nemesis, 1990, he imagined a planetary system around a wandering star hidden near our own. Though framed more in terms of a rogue star than a planet, the sense is the same: hidden wanderers, drifting nearby, reshaping our destiny without warning. The very title, Nemesis, recalls ancient myths of shadowy companions and dark intruders. Film has not ignored them either. In Lars von Trier's Melancholia, 2011, a rogue planet on a collision course with Earth becomes a metaphor for depression, inevitability, and human fragility. The rogue planet is not just a physical threat. It is the embodiment of despair, the crushing weight of cosmic inevitability. The haunting image of a silent, massive world emerging from the darkness captures the essence of why rogue planets resonate. They are powerful symbols of forces beyond control and of isolation that swallows light itself. Even beyond science fiction, myths of wandering worlds echo the concept. Ancient cultures often imagined dark companions or gods cast out of the heavens. The Greeks gave us the word planet, meaning wanderer, and while they thought of them as lights, the metaphor of wandering was already charged with unease. To wander is to lack a home, to be unmoored. Rogue planets are the ultimate wanderers, literalizing a metaphor humans have used for millennia. The symbolism of being without a sun is rich. A sun is more than a ball of plasma. It is warmth, guidance, stability, a clock, and a hearth. To lose it is to lose order. A planet without a sun becomes a metaphor for exile, for existing outside the warmth of belonging. Literature and philosophy alike use darkness as a stand-in for isolation, and rogue planets embody that perfectly. They are cosmic outsiders. They remind us of what it feels like to drift, to be cut loose from family, from society, from meaning. At the same time, there is resilience in the metaphor. To exist without a sun is to endure despite abandonment. A rogue planet continues, regardless of exile. It carries its mountains, oceans, and storms with it. It persists in the darkness. For some, that persistence is heroic. For others, it is tragic. Both readings are valid, and both appear in the stories we tell. Philosophically, rogue planets touch something primal in us: the fear of loneliness. Human beings are social, tied to families, communities, stars of our own. To imagine being cut off, drifting alone, is to confront the possibility of cosmic solitude. When astronomers say there may be more rogue planets than stars, the metaphor sharpens. The universe is not only full of suns and their loyal companions, it is full of outcasts. Solitude, then, is not an anomaly. It is a common fate. This resonates with existential philosophy. Thinkers like Jean-Paul Sartre and Albert Camus describe the human condition as one of being cast into an indifferent universe, without inherent meaning, forced to create our own. Rogue planets are cosmic metaphors for that condition. They are alone, without guidance, without light, and yet they continue. In them, we see a mirror of our own situation. Tiny beings on a tiny world, drifting through a galaxy that does not notice us, yet surviving, creating, insisting on meaning. The theme of exile also runs deep. Exile has always been one of humanity's deepest wounds. Banishment from home, from community, from belonging. Religious texts are filled with stories of exile, from Adam and Eve leaving Eden to the Israelites wandering the desert. Rogue planets are exile made physical, worlds torn from their homes, wandering forever in a wilderness without return. Their existence gives the old metaphor new teeth. Exile is not just human, it is cosmic, and yet there is also beauty in the image. To picture a rogue planet is to picture a world beneath eternal stars, skies darker and sharper than anything we know. It is to imagine oceans sealed under ice, glowing faintly from vents, life perhaps stirring in secret. There is tragedy, but there is also awe. If exile can still hold life, if solitude can still cradle beauty, then rogue planets become symbols not only of loneliness, but of hidden resilience. In this way, human imagination splits in two directions. On one hand, rogue planets are ominous, harbingers of doom, destroyers on collision courses, metaphors for despair. On the other, they are mysterious havens, secret worlds carrying hidden oceans, exiles that remind us that life finds a way. This duality is part of their allure. They are both the nightmare of isolation and the dream of survival against odds. Philosophy leans into both sides. To some, rogue planets are symbols of nihilism. The universe is cold, indifferent, and exile is our destiny. To others, they are symbols of defiance. Life can persist even without a sun. They embody the paradox of existence, lonely yet enduring, cast out yet still moving, dark yet carrying the possibility of light from within. This may explain why they fascinate us so deeply. Rogue planets are more than astronomical curiosities. They are canvases for our imagination, mirrors of our fears and hopes. They are reminders that the universe is not designed for our comfort, but also that we have always found meaning in wandering. We are, after all, wanderers ourselves, descendants of nomads, migrants across continents, explorers of oceans, dreamers of stars. The rogue planet is not only the other, it is us. When we think of them now, billions drifting in silence, it is easy to feel small, but it is also possible to feel kinship. We too are adrift, on a fragile sphere orbiting a modest star, in a galaxy that does not know we are here. In that sense, Earth is not so different. We are not exiles yet, but we are wanderers, and perhaps one day our descendants will leave the sun behind, carrying their worlds with them, becoming rogues by choice, exiles by ambition. The line between science and imagination blurs here. Rogue planets exist, and their statistics are scientific. But their meaning, their symbolism, is human. They tell us as much about ourselves as they do about the cosmos. They are reminders that science is not only about numbers and equations, but about wonder, fear, philosophy, and poetry. In the end, rogue planets are both physical realities and metaphors written across the night sky. When we speak of life in the universe, we usually frame it in terms of sunlight, the habitable zone around a star, the so-called Goldilocks zone, is defined by how far a planet can orbit without being too hot or too cold for liquid water on its surface. It is a simple, almost comforting picture. Each star has a narrow belt where worlds might be like Earth, basking in warmth, fertile with oceans, green with potential. For decades, this model shaped our thinking about life beyond Earth. But rogue planets complicate this picture. They live outside the very definition of a habitable zone. They drift in deep space, receiving no sunlight, their skies forever black. By traditional standards, they should be sterile. And yet, over the past half-century, scientists have learned that life is far more flexible than we once thought. The discovery of ecosystems thriving around hydrothermal vents in the late 20th century changed everything. Here, in total darkness, microbes extract energy not from sunlight, but from chemical reactions, converting hydrogen sulfide and other compounds into food. On Earth, sunlight drives the grand majority of biology, but not all of it. Some life thrives in places where the sun might as well not exist. Rogue planets, then, are not immediately disqualified. Instead, they invite a question. Could life survive in permanent night? Astrophysicist David Stevenson addressed this possibility in 1999. He proposed that rogue planets could retain thick hydrogen atmospheres, insulating them so effectively that liquid water might exist on their surfaces, even without a star. In his model, such a planet would trap geothermal heat and recycle it through convection, creating a faint but sufficient greenhouse effect. It would not be a sunlit paradise, more a dim, warm world wrapped in haze, but it could sustain water and perhaps, in time, biology. Eric Abbott and Daniel Switzer extended this idea in the early 2000s, exploring whether free-floating planets might be easier to detect in infrared light than expected. Their calculations suggested that rogue planets with hydrogen blankets would not only glow faintly, but could also be relatively common. If billions of them drift through the Milky Way, then billions of potential microbial incubators drift with them. The implications are staggering. For decades, astrobiology clung to the rare Earth hypothesis, suggesting that life requires the fragile balance of a star and planet in harmony. Rogue planets whisper something different, that life may not be tethered to stars at all. If microbial life can thrive on chemistry alone, then the universe might be far more fertile than our narrow definitions have allowed. Imagine a rogue Earth cast out of its solar system. Its surface freezes quickly, but under the crust, radioactive decay keeps the mantle hot. Oceans remain liquid beneath kilometers of ice, warmed by vents. Microbes arise near these vents, feeding on chemical gradients, slowly diversifying. Over billions of years, ecosystems spread throughout the subsurface ocean, evolving complexity in complete darkness. To them, sunlight is a myth that never existed. For such life, the rogue planet is not exile, it is home. The parallels with Europa and Enceladus make this plausible. Both moons exist well outside the solar habitable zone, yet both harbor liquid water beneath ice. Cassini's flybys of Enceladus revealed plumes of water vapor, salts, and organic molecules, suggesting not only an ocean, but also hydrothermal activity. Europa, too, shows signs of a salty global ocean, stirred by tidal heating. Neither depends on sunlight. Both depend on geology and chemistry. Rogue planets are simply larger canvases for the same recipe. This idea broadens not only our concept of habitability, but also the scope of panspermia. Panspermia is the hypothesis that life, or at least its building blocks, can spread through space, carried by meteorites, comets, or other bodies. Traditionally, panspermia has been imagined between planets in the same system, say, microbes blasted from Mars surviving the journey to Earth. But rogue planets extend the scale. If these bodies wander the galaxy for billions of years, could they carry life from one system to another, acting as interstellar arcs? It is not as implausible as it sounds. When meteorites strike a planet, debris is ejected into space. Some of this debris could land on a rogue planet during a close pass near a star system. If that rogue already hosts subsurface oceans, the imported material might add genetic diversity or even spark a new biosphere. Likewise, if a rogue planet carried life of its own, fragments blasted from it could seed other systems during a near encounter. In this way, rogue planets might be vectors of life moving slowly but persistently across the galaxy. They are not fast messengers like comets, but long-term carriers, drifting for eons before encountering another system. Each one could be a capsule of chemistry, a slow arc in an ocean of stars. Of course, many scientists remain cautious. The challenges are immense. Rogue planets are dark, hard to detect, and harder still to study. To know whether they harbor life is beyond our current reach. Even if they exist in vast numbers, their oceans are sealed under ice, inaccessible to telescopes. Yet scientific caution does not erase the possibility, it only sharpens the questions. If rogue planets can support life, the implications ripple through astrobiology. First, the probability of life elsewhere skyrockets. Instead of life being confined to narrow stellar zones, it might thrive in environments unbound to stars. Second, it suggests that life's persistence does not depend on external conditions as much as internal processes. Energy, water, chemistry, these are enough. And third, it reframes the universe not as a desert of light, but as a vast archipelago of hidden worlds, each a possible experiment in biology. There is also a philosophical echo here. If life exists on rogue planets, it is life that survives without the obvious warmth of the cosmos. It is life that thrives in solitude, without ever knowing the stars. For us, raised under sunlight, that is difficult to imagine. But for such life, exile is not exile. Darkness is not loneliness. It is simply the condition of existence. The more we contemplate it, the more rogue planets challenge our assumptions. For centuries, humanity believed itself to be central, then at least luminous, life clinging to a star's light. To realize that life might just as easily thrive in the dark is humbling. It suggests that biology is not rare, not fragile, not bound to warmth and brightness. It is flexible, opportunistic, as ready to thrive in black oceans as in sunlit shallows. The galaxy, then, may be teeming not only with visible worlds circling stars, but with invisible worlds carrying invisible ecosystems. Every starless gap in the night sky may hide more life than we suspect. Perhaps the nearest extraterrestrial biosphere is not around another star at all, but drifting silently between them. A rogue planet with seas beneath ice, microbial colonies clinging to vents, alien yet oddly familiar. And if life does spread by panspermia, then rogue planets may even connect us. Life on Earth could share ancestry with life on a wandering world, seeded long ago, separated by eons, yet cousins in the deepest sense. To contemplate this is to feel less alone, even in the silence of space. For now, all of this remains speculation. We have no probe to drill through the crust of a rogue planet, no telescope to see inside its hidden seas. We work with analogies, Europa, Enceladus, Earth's vents, and with equations of heat and chemistry. But speculation, when rooted in science, is more than fantasy. It is a map of what to look for. It prepares us for the surprise of discovery. If rogue planets harbor life, then exile is not emptiness. It is abundance, hidden in plain darkness. The cosmos, then, is not just a theatre of stars, but a sea of wanderers, some carrying within them the oldest story of all: life adapting, enduring, surviving. Perhaps one day we will confirm it. Perhaps one day we will send instruments into interstellar space, not just to study stars, but to chase shadows, to catch a drifting world and listen for its secrets. Until then, rogue planets remain both scientific mysteries and philosophical mirrors, reminders that life may be lonelier, stranger, and more resilient than we ever dared to think. When we think of rogue planets, it is tempting to picture them as distant curiosities, silent wanderers adrift in interstellar space, far from our concerns. But the truth is less comforting. If there are billions of these bodies in the Milky Way, then some must, sooner or later, pass near our solar system. And if one were to come too close, the consequences could be profound. The thought has haunted astronomers and writers alike. What happens when a dark world wanders into our neighborhood? The galaxy is not static. Stars themselves drift through it, carried by galactic orbits, sometimes passing relatively close to one another. Our Sun, too, moves through this ocean, occasionally brushing against the gravitational influence of other stars. On a cosmic timescale, encounters are inevitable. Already, we know of past and future close passages. About 70,000 years ago, a dim red dwarf known as Schultz's star passed through the outer Oort cloud, the icy shell of comets at the edge of our solar system. It was too small and too far to disturb much, but it was a reminder: we are not isolated. Stars, and whatever planets they may carry, wander through our vicinity from time to time. Now imagine that instead of a faint star, it was a rogue planet, a world the size of Jupiter, invisible until it blocked a background star or disturbed cometary orbits. Such an encounter could wreak havoc. Even without colliding with Earth, the gravity of a massive rogue passing nearby could tug on our planets, altering orbits, destabilizing the delicate balance we rely on. In simulations, even a grazing pass could send comets raining inward, disturb Earth's seasons, or in extreme cases, fling our world into a new orbit or into exile as a rogue itself. Astronomers, aware of these possibilities, have occasionally wondered if such intruders might explain mysteries in our own solar system. This is where the stories of Nemesis, Planet X, and Tyche enter, half scientific, half speculative, always fueled by the unease that maybe something lurks in the dark. The Nemesis hypothesis arose in the 1980s. Paleontologists had noticed what they thought were periodic mass extinctions in Earth's fossil record, die-offs every 26 million years or so. To explain this, some astronomers suggested that a faint companion star to the Sun, dubbed Nemesis, might orbit far out in the Oort cloud. Every so often, as it swung close, its gravity would disturb comets, sending showers toward Earth and triggering extinctions. The idea captured imagination. It explained both the supposed cycles and our inability to see such a faint companion. But as evidence piled up, the regularity of extinction events was questioned, and searches for Nemesis turned up nothing. Today, most astronomers consider it unlikely. But the idea of a hidden wanderer disturbing Earth's fate lingers in memory, a ghost of how rogue visitors might reveal themselves. Planet X is another ghost in this gallery. The term was coined in the early 20th century by Percival Lowell, who believed discrepancies in Uranus and Neptune's orbits suggested another planet beyond them. This search eventually led to the discovery of Pluto in 1930, though Pluto turned out to be far too small to explain the supposed anomalies. For decades afterward, the idea of Planet X remained alive, a hidden giant lurking at the edge of the solar system. Modern calculations, based on better data, resolved most of Lowell's discrepancies, but the name stuck. Even today, when astronomers speak of possible new planets in the outer solar system, they still call them Planet X. Tyche was a more recent version of this suspicion. In the 2010s, some astronomers suggested that data from the WISE infrared survey might hint at a giant planet in the Oort cloud. perhaps several Jupiter masses, wandering unseen. The name Tyche, after the Greek goddess of fortune, was chosen to distinguish it from Nemesis. But subsequent analyses showed no such planet. Tyche, too, was relegated to speculation. Yet speculation persists because the possibility is real. We know that rogue planets exist. We know that stars pass close to one another. We know that gravity is merciless when large bodies interact. To imagine a rogue intruder is not fantasy, it is an extrapolation of what must occasionally happen. If a rogue planet were to approach the solar system, the effects would depend on its mass and trajectory. A small rogue, Mars-sized or less, passing through the outer regions might do little beyond stirring comets. But a giant like Jupiter could reshape everything. Its gravity might disrupt the Kuiper belt, scattering objects inward. It could alter Neptune's orbit, ripple disturbances inward to Uranus, Saturn, and even Jupiter itself. Over millions of years, those ripples could destabilize the inner system, changing Earth's orbit. A shift in orbital eccentricity or tilt could alter climate dramatically, triggering ice ages or heat waves. In extreme cases, Earth could be pulled out of the habitable zone entirely, or ejected as a rogue itself. Closer encounters would be catastrophic. If a rogue passed near Earth, tidal forces could stretch the planet, triggering earthquakes and volcanic eruptions. A collision is unlikely, given the vastness of space, but not impossible. A direct impact with a Jupiter-sized rogue would annihilate Earth completely. Even a smaller one, the size of Mars, could sterilize the biosphere. Some scientists have speculated that rogue intruders might even explain mysteries in the solar system's past. Why is Uranus tilted on its side? Perhaps it suffered a collision with a large wandering body. Why does the Kuiper belt appear truncated? Perhaps an intruder passed by long ago, scattering away much of its population. We cannot prove these ideas, but they remind us that intruders are not only possible, they may already have left their fingerprints. For Earth itself, the probabilities are small, but not zero. Estimates suggest that a rogue planet might pass within 1 light-year of the Sun every few million years. A close approach within the Oort cloud is more likely, disturbing comets and sending some toward Earth. A direct pass through the planetary region is far rarer, perhaps once every tens of billions of years, but the timescales of the galaxy are long. What is unlikely in a human lifetime is almost inevitable in cosmic time. When the idea of Nemesis captured public imagination in the 1980s, part of its appeal was existential. It suggested that extinction was not random, but written into the structure of the cosmos. A hidden companion dictated our fate. Today, even as Nemesis itself has been discarded, rogue planets revive that unease. Perhaps extinction is not only written into Earth's geology or biology, but into the wandering of stars and planets themselves. The cosmos does not guarantee permanence. Orbits are fragile. Stability is temporary. And yet, there is something awe-inspiring about this fragility. The fact that Earth has survived billions of years without catastrophic disruption is itself remarkable. Perhaps we have been lucky. Perhaps our position in the galaxy has sheltered us. Or perhaps rogue encounters are less destructive than we fear. After all, the solar system has endured close passes before, Schultz's star, others now predicted in the future, without disaster. Maybe exile is common, but survival is too. Still, the possibility sharpens our imagination. It appears in literature again and again. Worlds struck by wandering bodies, civilizations undone by intruders from the dark. Films like Melancholia or When Worlds Collide dramatize the terror of a rogue approach, using the image of a looming planet to symbolize fate itself. In truth, the physics is subtler and slower. Gravitational nudges, orbital instabilities unfolding over millennia. But the fear is the same. that we are not as secure as we think, that the night sky hides not only stars, but shadows moving toward us. If a rogue planet were ever detected on a near approach, the human response would be extraordinary. Unlike comets or asteroids, which we might deflect, a planet is unstoppable. We could not nudge a world of Jupiter's mass out of the way. Our only options would be adaptation or escape, terraforming technology far beyond us, or starships to flee. In such a scenario, exile would become our fate, just as it is for the rogues themselves. We would become wanderers, leaving the sun behind to survive. Philosophically, the idea of rogue visitors forces us to confront impermanence. Earth feels eternal, the sun reliable, but both are vulnerable to forces outside themselves. A passing planet could undo billions of years of history in an instant. This fragility is unsettling, but also clarifying. It reminds us that stability is precious, that life on Earth thrives within a narrow window of cosmic calm. We exist not because the universe guarantees safety, but because we have so far been spared its chaos. And yet, chaos is never absent. The rogue planets drifting through the galaxy are reminders of that. They are warnings written in darkness. The cosmos is not a safe harbor. It is a sea filled with hidden giants, silent until they pass close enough to stir tides and shift destinies. But perhaps that is part of their meaning. Rogue planets are not only symbols of exile and loneliness, they are also symbols of humility. They remind us that the universe is larger than our certainties, more dangerous than our routines, and more beautiful than our fears. To know that a dark planet could, one day, appear in our skies is terrifying. But to know that billions of them wander unseen, indifferent to us, is also a kind of wonder. In the end, rogue visitors are both threat and mirror. They may never pass close enough to destroy us, but their possibility reshapes how we see ourselves. We are not permanent. We are not guaranteed. We are one world among billions, surviving for now in the grace of stability. Tomorrow, or a million years from now, that stability could end. And in that truth lies both fear and perspective. The cosmos, filled with rogue wanderers, is not built for our safety. It is built for motion, for exile, for drift. We are lucky to have found light. But light is not eternal, and darkness is always moving toward us. When we look up at the night sky, it is easy to think of stars as the dominant feature of the galaxy. Billions of them glitter in the Milky Way, each a beacon of energy, each commanding its own space. For centuries, astronomy was almost entirely the study of stars, their motions, their colors, their births and deaths. Planets, if thought of at all, were assumed to be rare, fragile attendants. The discovery of exoplanets shattered that view. We now know that planets are not exceptional, but ordinary, so common that nearly every star likely hosts some. But rogue planets push the lesson even further. They remind us that the galaxy is not only a city of stars, it is also a wilderness of dark, drifting worlds. The question, then, is how many of them exist. The numbers are staggering. In 2011, based on microlensing surveys by OGLE and MOA, astronomers estimated that Jupiter-sized rogue planets might be at least as common as stars in the Milky Way. That meant perhaps 400 billion or more wandering without suns. Later, refinements suggested an even larger population, perhaps 2 rogue planets for every star. If correct, then our galaxy alone could contain more than 1 trillion of them. 1 trillion worlds, adrift in silence. That number is so large, it resists imagination. To bring it down to scale, between the Sun and the nearest star, Proxima Centauri, there might be dozens of rogue planets scattered invisibly across the void. The night sky we see, with its familiar constellations, is only a fraction of what is truly there. Hidden between the lights are countless unseen spheres, each with its own geology, chemistry, perhaps even oceans or atmospheres, drifting unseen. These numbers come not from idle speculation, but from careful statistics. Micro-lensing events, though rare, provide a way to estimate populations. By monitoring millions of stars and counting how often their light is briefly magnified, astronomers can infer how many unseen objects are crossing our line of sight. When the timescale of the event suggests an object too small to be a star or brown dwarf, the culprit is likely a planet. By analyzing the frequency of such events, scientists can estimate how common rogues are. The numbers, though uncertain, consistently point to vast populations. Simulations of planetary formation support these statistics. When astrophysicists model young planetary systems, they see chaos. Early disks are crowded, with many planetary embryos jostling for space. Collisions are frequent, migrations common. In such an environment, gravitational scattering is inevitable. Some bodies spiral inward, consumed by the star. Others are hurled outward, never to return. Ejection, it seems, is not a rare accident, but a normal part of planetary birth. Consider our own solar system. Some models of its early history suggest that it once contained an additional giant planet, perhaps Neptune-sized. In simulations, this world often ends up ejected, cast into interstellar space by interactions with Jupiter and Saturn. If true, then even our orderly system bears scars of exile. Multiply this process across hundreds of billions of stars, and the result is a galaxy thick with castaways. Galactic dynamics amplify the effect. Young stars are often born in clusters, crowded neighborhoods where stellar siblings tug at each other's systems. A passing star can destabilize outer planets, flinging them away. Over millions of years, these encounters add up, scattering planets into the galaxy. Even mature systems are not immune. As stars drift through the Milky Way, their gravity brushes against one another, subtly reshaping distant orbits. The galaxy is not a static backdrop, but a restless ocean, and in that ocean, worlds are often swept loose. The implication is profound. Planetary systems are not stable fortresses. They are leaky, fragile, constantly shedding members. For every world that remains loyally bound to its star, there may be others that slipped away long ago. When we picture a solar system, we imagine neat orbits, planets circling forever. The reality is closer to a storm: collisions, migrations, expulsions, and only a fraction of bodies surviving in long-term harmony. This reframes how we think about our own place. Earth feels secure, locked in orbit around the Sun, but stability is not guaranteed. It is contingent. Our orbit, though steady now, is the result of billions of years of fortunate dynamics. With slightly different initial conditions, Earth might have been scattered, just another rogue in the dark. That we are not is a stroke of cosmic luck. The instability of planetary systems is not merely theoretical. We see its evidence everywhere. Exoplanet surveys reveal systems with hot Jupiters, gas giants improbably close to their stars, clearly migrated inward. Others show eccentric orbits, tilted planes, resonances suggesting past chaos. In many of these cases, one can almost hear the echoes of planets that are no longer there, expelled in the violence of youth. The rogues we count are the fossils of that process, the survivors of gravitational battles lost. Even the scale of rogue planets varies. Some are giants, masses of hydrogen and helium comparable to Jupiter. Others may be rocky, Earth-sized bodies. Microlensing hints at both. Smaller rogues are harder to detect, but simulations suggest they may be more numerous because smaller planets are more easily ejected. If so, then the majority of rogue planets in the galaxy might be Earth-sized or smaller, worlds like ours cast out into eternal night. That thought is haunting. Billions of Earths, frozen, drifting, invisible. What does this tell us about planetary systems? First, that they are prolific. Stars do not form with one or two planets. They form with many, and some are lost. Second, that they are unstable. Order is rare, chaos the rule. And third, that the galaxy is richer in planets than stars, perhaps by a wide margin. Planets are not jewels but pebbles, abundant and expendable, tossed about by gravity's currents. This abundance reshapes the way we think of habitability. If rogue planets number in the trillions, then even if only a tiny fraction harbor subsurface oceans, the total number of habitable niches may be immense. Our old picture of life, clinging only to rare Earths in narrow habitable zones, may be far too pessimistic. The galaxy may be full of hidden biospheres, invisible in darkness, but real nonetheless. The numbers also sharpen the sense of cosmic danger. If rogue planets are so common, then some must occasionally pass near stars, disturbing their systems. The Milky Way is dynamic, and close encounters are part of its fabric. Our survival is not eternal, it is fortunate. Each rogue planet is a reminder of that fragility. In a sense, the statistics of rogues are the statistics of exile. They tell us that exile is not exceptional, but normal, that planetary systems are not permanent homes, but temporary arrangements. Every system carries within it the seeds of instability. Every star is surrounded not only by loyal companions, but by potential exiles waiting to be cast out. The galaxy is a theatre not only of creation, but of loss, and the rogues drifting between stars are the evidence of that. Yet in this loss, there is also perspective. To know that planets can be exiled is to see the cosmos as it is, dynamic, unstable, alive with motion. To know that there may be more rogue planets than stars is to realize that the universe is richer than we imagined, not emptier. What seems like loneliness, worlds without suns, may in fact be abundance. Countless hidden stages for stories of geology, chemistry, perhaps even life. So how many rogue planets exist? The answer is vast beyond comprehension. Perhaps hundreds of billions, perhaps trillions, enough to outnumber stars 2 to 1, or even more. Enough that between us and the nearest star, unseen neighbors drift. Enough that every patch of sky hides not just suns, but invisible worlds. And what does this tell us about planetary systems? That they are not eternal clocks, but restless storms. That exile is part of birth, not its exception. That stability, when it occurs, as with Earth, is rare and precious. And that the universe, though it looks orderly from afar, is in fact a place of constant loss, constant scattering, constant wandering. The Milky Way is not only a city of stars, it is also an ocean of dark worlds, more numerous than the lights we see, drifting forever in silence. And in that realization, our picture of the cosmos is transformed. We are not living in a galaxy of suns surrounded by loyal companions. We are living in a galaxy of exiles, where wandering is the rule and belonging the exception. For most of human history, rogue planets were unthinkable. Planets were defined by their loyalty, by their orbit around a star, their place in a cosmic family. Only in the past few decades have we learned that exile is just as common as belonging. And yet, despite this revelation, we still stand at the threshold of ignorance. We know rogue planets exist. We suspect they may outnumber the stars. But beyond the handful detected by microlensing and the hints from infrared surveys, we have no catalogue, no census, no detailed knowledge of their diversity. We know the shadows are there, but we have not yet seen their faces. That is about to change. The coming generation of telescopes, spaceborne and ground-based, promises to revolutionize our view of these hidden wanderers. The age of rogue planet discovery is only beginning, and the frontier ahead is one of the most mysterious in astronomy. The most anticipated instrument for this task is NASA's Nancy Grace Roman Space Telescope, scheduled for launch later this decade. Roman is often described as Hubble's wide-eyed cousin. While Hubble focused on narrow, detailed views of galaxies and nebulae, Roman will have a much wider field of vision, able to monitor vast swaths of the sky at once, with exquisite precision. Its key strength for rogue planet hunting lies in its microlensing survey. Gravitational microlensing, Einstein's quirk of spacetime, has already given us hints of rogue planets, but current ground-based projects like OGLE and MOA face limitations: atmospheric interference, weather, and the sheer difficulty of monitoring millions of stars continuously. Roman, observing from space, will remove those obstacles. Its detectors, combined with its broad field, will capture thousands of microlensing events in the crowded star fields of the Milky Way bulge. Among those events, many will be caused not by stars, but by planets, bound and unbound alike. Roman is expected to detect hundreds of rogue planets, spanning a wide range of masses, from giants like Jupiter down to worlds as small as Mars, perhaps even Earth. For the first time, we will have not just statistics inferred from short lensing events, but a direct, consistent survey. Roman's catalogue will allow astronomers to map the distribution of rogue planets, their sizes, their frequency, their place in galactic architecture. We may learn whether Earth-sized rogues are common, whether giant ones dominate, or whether there is a spectrum across the whole planetary mass range. Alongside Roman, Europe's Euclid mission, launched in 2023 to study dark matter and dark energy, will also contribute. Euclid's deep, wide-field surveys are designed to map the geometry of the universe, but its precision photometry will inevitably detect microlensing events as well. Like Roman, it will peer into the crowded regions of the galaxy where rogue planets are most easily revealed. In combination, Euclid and Roman will transform microlensing from a niche technique into a primary tool for understanding unseen worlds. Ground-based telescopes, too, are advancing. The Vera C. Rubin Observatory in Chile, with its Legacy Survey of Space and Time, LSST, will repeatedly scan the sky with unprecedented depth and cadence. While its main goals include studying dark energy and cataloguing asteroids, LSST will also be a factory for transient events, including microlensing. Its vast dataset may catch rogue planet signals, complementing the space-based missions. Other ground-based arrays, increasingly equipped with adaptive optics to counter atmospheric distortion, will help confirm and refine discoveries. Infrared astronomy is another frontier. Rogue planets, especially young ones, glow faintly in infrared as they radiate leftover heat from formation. Telescopes like the James Webb Space Telescope, JWST, already have the sensitivity to detect some of these faint embers in nearby star-forming regions. By distinguishing low-mass brown dwarfs from planetary mass objects, JWST may directly image isolated rogues, giving us our first real glimpses of them. Future infrared observatories, perhaps even larger than JWST, could expand this search, identifying rogue planets across greater distances. Together, these tools herald a new era, the transition from speculation to census. Instead of a handful of fleeting detections, we will have catalogues, distributions, and demographics. For the first time, rogue planets will take their place in the statistical landscape of the galaxy, not as rumors, but as mapped populations. The impact will ripple across astrophysics. First, it will refine our understanding of planetary formation. By comparing the abundance of rogues of different masses, scientists can test models of scattering and ejection. If small rogues vastly outnumber giants, it will confirm that ejection preferentially targets lower mass worlds. If giants are common, it will imply violent early dynamics. The ratios of rogue planets will become fingerprints of how systems form and evolve. Second, the discoveries will inform astrobiology. If Earth-sized rogues are common, the number of potential hidden habitats, skyrockets. Romans data could provide the first hard numbers on how many possible havens for life drift in the galaxy. Though we cannot probe their oceans directly, knowing their abundance reshapes the probabilities. Life, in this view, becomes not a rare exception, but a statistical expectation. Third, the data will contribute to our knowledge of galactic mass distribution. Rogue planets, though tiny compared to stars, are so numerous that they contribute measurable mass to the Milky Way. Understanding their distribution will help refine models of galactic dynamics. They will not explain dark matter, there are not nearly enough, but they are part of the visible scaffolding of the galaxy. There is also the frontier of direct detection, the dream of actually seeing a rogue planet in detail. Infrared telescopes may eventually capture spectra of their atmospheres, detecting water, methane, or hydrogen blankets. If that day comes, we will not just infer that life is possible, we will begin to test those possibilities directly. For now, it remains a dream, but a dream that technology steadily moves closer to. This new field, sometimes called dark astronomy, is about more than rogue planets. It includes brown dwarfs, failed stars, faint stellar remnants, all the hidden objects that make up the unseen majority of the galaxy. But rogue planets are perhaps its most haunting members. They are the epitome of the unseen, worlds without light, detectable only by the subtlest bending of starlight or the faintest glow of heat. They embody the shift in astronomy from studying only what shines to studying what hides. Philosophically, the coming discoveries will change how we imagine the galaxy. The Milky Way will no longer be pictured as a disk of stars surrounded by emptiness. It will be seen as a crowded ecosystem, a sea where every gap between suns holds invisible planets. The poetry of this image is almost overwhelming. Our galaxy, once thought sparse, is revealed as teeming with unseen worlds, wandering forever in darkness. It is worth pausing to reflect on how extraordinary this is. A century ago, no one knew exoplanets existed at all. 30 years ago, the first orbiting an ordinary star was confirmed. 20 years ago, rogue planets were still speculative. Today, we speak of counting them by the hundreds and thousands, mapping their distribution, testing their theories. The pace of discovery is dizzying, and with Roman, Euclid, Rubin, and JWST, the next decade may reveal more about these hidden wanderers than all of human history before it. What we will learn may surprise us. We may find that rogue planets are even more abundant than predicted. We may discover populations of small rogues that dwarf the giants in number. We may detect their faint atmospheres, confirming theories of hydrogen blankets and subsurface oceans. Or we may uncover mysteries we have not even imagined, populations that defy our models, objects that blur the line between planet and star, worlds unlike anything in our solar system. That is the frontier of dark astronomy, the promise that the unseen will be revealed, and that in revealing it, our picture of the universe will be transformed. The rogue planets are waiting, silent, invisible, patient. They drift through the galaxy, indifferent to our curiosity. But we, fragile creatures of light, are determined to find them. With lenses of glass and mirrors of silver, with sensors cooled to near absolute zero, with equations derived from Einstein and tested against starlight, we will catch their shadows. We will count the exiles. We will map the wanderers. And in doing so, we will expand not only our science, but our imagination. The future of rogue planet research is not simply about discovery. It is about redefining what it means to live in a galaxy. It is about recognizing that the night sky hides more than it reveals, that between every star there are worlds beyond counting. It is about accepting that the cosmos is not only a place of shining suns, but of darkness, and that the darkness too has stories. In the coming years, we will hear those stories. Roman, Euclid, Rubin, JWST. They are our ears pressed against the cosmic silence, listening for the whispers of worlds without suns. And when the data arrives, when the first true catalogue of rogue planets is laid before us, it will not only satisfy curiosity, it will change how we see ourselves, not as inhabitants of a rare sunlit island, but as neighbours in a galaxy overflowing with exiles. The frontier is vast, the tools ready, the discoveries imminent. The dark will not remain silent forever. To speak of rogue planets is to speak not only of astronomy, but of metaphor. They are real, physical worlds, drifting through the galaxy in silence. Yet they also carry with them an unmistakable symbolic weight. More than most astronomical objects, they seem designed for reflection. They are metaphors written across the dark: solitude, resilience, wandering. A star is a symbol of belonging. It holds a family of planets, provides warmth, dictates order. But a rogue planet is a symbol of exile. It has been cast out or born alone, with no center to orbit, no light to bask in. It drifts, unmoored, across a galaxy that may not even notice it. When we think of such a world, we cannot help but see echoes of ourselves. Human beings know what it is to feel cast out. We know what it is to feel alone, to move through life without a center. Cultures have long told stories of exiles, wanderers, outcasts. Cain, condemned to wander the earth. Odysseus, adrift for years away from home. The Jewish diaspora, the Romani journeys, the nomadic migrations of countless peoples. Exile is not only personal but cultural, written into our oldest myths. Rogue planets take those stories and etch them into the cosmos itself. They remind us that exile is not just a human condition, it is cosmic. Worlds themselves can be exiles. Yet exile is not only loss, it is also resilience. A rogue planet, cut off from its star, does not simply vanish. It continues, carrying its oceans, its crust, its chemistry. It continues to orbit the galaxy, quietly, persistently. It endures, and endurance is its own kind of poetry. It tells us that life, whether biological or planetary, does not always need warmth and light. Sometimes it needs only persistence, momentum, resilience. In this way, rogue planets become not just symbols of loneliness, but of survival against odds. The philosopher Albert Camus spoke of the absurd, the confrontation between human desire for meaning and the indifference of the universe. His famous metaphor was Sisyphus, condemned to roll his boulder forever. But perhaps the rogue planet is an even better symbol. It drifts in indifference, denied the comfort of a star, yet it keeps going. It does not despair. It does not surrender. It simply continues, orbiting the galaxy on its own path. To imagine such a world is to imagine the purest expression of resilience, a being without light, yet still existing. This dual symbolism, loneliness and resilience, explains why rogue planets haunt our imagination. Literature has cast them as destroyers, intruders, omens of doom. But it has also cast them as mysterious havens, secret worlds where life might survive in the dark. They are outsiders, and humanity has always been fascinated by outsiders. We define ourselves by who belongs and who does not. We tell stories of the rebel, the exile, the wanderer. Rogue planets are those stories scaled up, given geological and cosmic form. There is also a beauty in their wandering. Most planets are bound, their paths predictable. But rogues have no such tether. They wander freely, carried only by their momentum and the gravity of the galaxy. They are cosmic nomads, explorers without intention. In them, we see something of our own wanderlust, the human urge to move, to travel, to see what lies beyond. We have always been a migratory species, restless, unwilling to stay still. Perhaps that is why rogue planets resonate so deeply. They mirror not only our fears of exile, but also our dreams of exploration. What would it feel like to stand on such a world? Imagine the silence, a sky filled with stars, sharper and brighter than we have ever seen, because no sun overwhelms them. The Milky Way arcing overhead in a brilliant band. No sunrise ever coming, no shadows shifting with time, only the slow drift of constellations over centuries, mountains under eternal starlight, oceans sealed beneath ice, volcanoes glowing faintly in the dark. It would be a place at once terrifying and sublime, beautiful in its alien constancy. A world without a dawn, but not without wonder. There is something deeply haunting about that image, but also comforting. Haunting, because it reminds us of how fragile our own sunlight is. Comforting, because it shows us that beauty is not dependent on light. Beauty can exist in darkness too. A rogue planet does not need a sunrise to be magnificent. Its magnificence lies in its endurance, in its quiet persistence through cosmic night. Perhaps that is the final lesson they offer us, that belonging is not the only path to meaning. We seek warmth, family, community, suns to orbit. But sometimes, meaning is found in resilience, in continuing even when cut loose. Rogue planets are metaphors not only of exile, but of the strength that exile demands. And they are not alone. There may be trillions of them. The night sky, though it looks empty, is crowded with wanderers. Each one is silent, invisible, but real. We may never see most of them, may never visit them, but we can imagine them, and in imagining them, we recognize something of ourselves. For humanity, the fascination with outsiders has always been double-edged. We fear them, and we envy them. We cast them out, and we follow their stories with longing. Rogue planets capture that paradox perfectly. They are frightening, giants in the dark that might one day disturb us. But they are also enviable, free, unbound, wandering. They remind us that even in exile, there is movement, there is possibility, there is beauty. So as we close this journey through rogue planets, the science of their formation, the methods of their discovery, the dangers they pose, the possibilities they carry, we return to the haunting image with which we began, a world without a sunrise. Picture it one last time, a lonely planet adrift, its surface frozen, its sky filled with unending stars. No dawn to anticipate, no warmth to arrive. And yet, beneath its crust, perhaps, an ocean stirs, kept alive by heat from within. Microbes cling to vents, weaving their quiet existence, unaware that they live in exile. Above them, the world drifts on, a ghost in the galaxy, alone yet enduring. That is the beauty of rogue planets. They are reminders that the universe is larger than our comforts, harsher than our imaginations, and yet more resilient than our fears. They are the outsiders of the cosmos, and in them we see both our vulnerability and our strength. A star rises over Earth tomorrow because gravity allows it. But somewhere else, in the silence of space, a world waits without sunrise, and still it turns. Thank you for drifting through this journey tonight. Rogue planets, silent wanderers without suns, remind us that the universe is full of mysteries hidden in its darkest places. Worlds adrift, carrying their own stories of exile, resilience, and quiet beauty. If you've made it this far, I'd love to hear from you. Tell us in the comments where you're listening from and what the sky looks like above you right now. And if you'd like more nights of discovery and reflection, consider subscribing. It helps keep this space alive. For now, let your thoughts rest. The stars will still be there tomorrow. And somewhere, in the deep quiet between them, rogue planets continue their endless journey. Good night.